class. This is the lesson for AP Physics 1 and IB week of May 17th. And the topic, we are continuing with our second lesson about fluids. Fluids! Fluids! Okay, and so just to review last time, what we did last time, we learned about some different properties of fluids. Fluids, such as density, which is mass divided by volume. Some fluids are compressible, some fluids are incompressible. We learned about pressure, which is the force per area. So if we think about like a submarine within the fluid, there's a certain force pushing on the walls of the submarine per area of the wall. That is pressure. And we learned that the pressure at a given depth is equal to P0, which is the atmospheric pressure, or the pressure at the top, at the surface of the fluid, plus the density of the fluid times the acceleration due to gravity times the depth. So what this means is that the deeper you go, the greater the pressure. Okay, and you can experience this if you dive down into a swimming pool. You can feel the increased pressure on your eardrums. A couple of common values. So the atmospheric pressure for Earth is 10 to the 5th pascals. A pascal is a Newton per meter. And then, so that's oftentimes used as P naught if you're doing any calculation on Earth. A couple of densities that are important. The density of air is 1.2 kilograms per cubic meter. All right. And the density of water, this is fresh water, is 1,000 kilograms per cubic meter. We also learned about the continuity equation, which says that basically if you have a tube of fluid and it narrows or it widens, the volume per second of fluid that is going into the pipe has to be the volume of fluid per second that is exiting the pipe, assuming that the pipe has no leaks. Okay, and the volume per second going in is area times speed, and so that's area of the input times speed at the input, and that has to equal the area of the output times the speed at the output. Okay, so this equation explains things like when you put your thumb over the hose, it sprays out faster because you're reducing the area, so the speed has to go up to compensate. It also explains things like river rapids. So why is the water shallow at the river rapids? It's because you are reducing the area, so the speed of the river has to go up to maintain a constant number of cubic meters per second of water flowing down the river. Okay? So that's what we learned about last time. This time, I want to talk about two things. The first thing I want to talk about is buoyancy, or the buoyant force. Okay, and so let's imagine that you have underwater. Okay, here's underwater. Here's the ocean floor. And you have some object, okay, that is in the water, okay, or in the fluid, okay. All right. Now that object is being pushed on by the fluid. In particular, the pressure at on the top is pushing the object down, okay? And the pressure at the bottom of the object is pushing the object up. Okay? But here's the thing. We know that the pressure increases with depth. So that means that there is more pressure, okay, on the bottom of the object than there is on the top, which means that there is more upward force than downward force. So that means that the net force due to all the pressures is upward. So the total force due to all the pressures pushing on the object is going to be upward, okay? Because the bottom of the object is deeper than the top, so the pressure on the bottom side is greater than the pressure on the top side, okay? So the buoyant force, that is the buoyant force. So the buoyant force is the force caused by pressure differential between the top and the bottom of the object. Okay? So there is a formula for the buoyant force, so I will call the buoyant force F sub B. All right, I'm not going to derive it. If you want me to explain why this is the formula, I will happily explain it to you, but I'm just going to give you the equation. So the formula for the buoyant force is rho v g. So let me explain what each of these terms is. So I'm going to add some subscripts. This is the density of the fluid. Okay? So this is the density of the fluid. Okay? All right. So, because keep in mind, when you're solving buoyancy problems, okay, when you're solving buoyancy problems, you have an object which has a certain density, and then you also have a the fluid surrounding it, which has a certain density. So the buoyant force is determined by the density of the surrounding fluid. Okay? This volume, I'm going to call it V sub D. And this is the volume of fluid displaced. Okay? And so that is really important. The idea of volume of fluid displaced by an object, okay? And this becomes particularly important if you have a something that is partially submerged. So for example, let's imagine a boat. Okay, so to explain the idea of volume displaced, let's imagine a boat. Okay. So you might have a boat, and so I'm kind of imagining the hull of the boat in cross section like that. Okay, and here's the water line. Okay, in this case, the volume displaced is the volume of fluid that is moved out of the way by the hull of the boat. So the volume displaced is going to be this volume right there, okay? So it's as if the water line continued and then that's going to be the volume displaced. So whatever that volume is, you would plug into there. Okay. Now here's something interesting. Okay, what if the boat got pushed below the surface of the water? Okay, so now you have the boat below the surface of the water like this. All right. Now, obviously, once the edge of the boat dips below the surface of the water, all the water is going to rush in to that space like that, right? So in that case, the only volume displaced is this volume right here. So you can see that what happens once a boat fully goes under the water will rush over this, rush over the sides and fill in this space with water, and then now the boat is displacing less volume, and so the buoyant force is reduced dramatically. So once its sides get below the surface of the water and water is allowed to rush in, the buoyant force will all of a sudden decrease dramatically. Okay. So that is something about buoyant force. Another interesting thing about buoyant force is it depends on the density of the fluid. We mentioned that salt water is denser than fresh water, so things are more buoyant in salt water. You might have actually noticed this before. It's actually a perceptible difference if you're swimming, and there are certain bodies of water. I want to say it's the Dead Sea that is like extremely salty, and you float very easily in the Dead Sea because the Dead Sea is very salty. The water is very dense because of that, and so there's a greater buoyant force. So that's kind of interesting. You can imagine a boat. What if a boat goes from salt water and then it drives into fresh water? In that case, the density of the boat, or the density of the fluid, will go down, right? Because it went from dense salt water to less dense fresh water. And because the density goes down, the buoyant force will get reduced, and that'll cause the boat to sink deeper into the water. So if you transition from salt water to fresh water, the boat will sink slightly deeper into the water. All right. G is, of course, the acceleration due to gravity. All right. So if we look at density of the fluid times volume, that's actually the mass of the fluid displaced. So the buoyant force is equal to the mass of the fluid that is displaced times gravity. And well, that is just the weight of the fluid displaced. Okay, so a lot of times you hear the buoyant force as the buoyant force is equal to the weight of the fluid displaced. All right. Okay. So, what is going to be the net force on an object that is in the water? Well, the net force on an object in the water, if we think about it, it has the buoyant force going upward, and then it has its own weight going downward. Okay, so the net force is the buoyant force minus the weight of the object, and that's going to be your net force. And you can actually set that equal to the mass of the object times its acceleration. And so you can get the acceleration of the object. Okay. So let's do a couple of problems with the buoyant force just to show how this works. So the first one is a hot air balloon. Hot air balloon must carry 200 kilograms. What is the radius of the balloon? Actually, we're not going to make this a hot air balloon. We're going to make this a helium balloon. Okay, so density of helium. I have to look up the density of helium. Gas. So the density of helium, so I just looked this up. The density of helium is roughly, why are there two values there? Okay. So helium, let me look this up. Sorry about this. Is 0.164 kilograms per cubic meter. Okay? So that is the density of helium. 0.164 kilograms per cubic meter. All right. So if we think about a hot air balloon, so here's the hot air balloon, and it has a little basket. All right. Okay. And the hot air balloon is surrounded by air. So air is the fluid that is providing the buoyant force. Okay. So the buoyant force is going to be equal to the density of the surrounding fluid times the volume displaced times gravity. So the density of the surrounding fluid is air, 1.2 kilograms per cubic meter. Okay. The volume of the balloon of the fluid that is displaced, we're going to assume that that volume is almost entirely coming from the balloon part, which is a sphere. Okay. So the basket does displace some air, but it's minuscule compared to the amount displaced by the entire hot air balloon. The volume of a sphere is 4/3 pi r cubed. And then gravity is 10. Okay? Actually, I didn't need this. I looked it up, but I remembered I don't need it. The balloon is carrying 200 kilograms. Okay? So that means that the weight of the balloon, including the helium inside it, is 200 kilograms. So that's 2,000 newtons, right? Because 200 kilograms times 10 meters per second squared for gravity is 2,000. Now, if the balloon is stationary, it's not dropping to the ground, it's not floating up into the sky, then these two have to be equal to each other. So we have to have 2,000 equals 1.2 times 4/3 pi r cubed times 10. And we can solve for r. So this says r cubed is the following. So that means that, well, I solved for r. So this is r cubed, so I'm going to have to take a cube root. And when I do that, I get 7.4 meters is the radius of the balloon. Okay? So that's pretty consistent with my experience. All right, so let's do another example. Let's suppose that you have a cylinder. A cylinder has radius let's say that the radius is actually, I take that back. Okay, so I'm going to change the problem slightly. Let's suppose that you have a canoe. Okay, a canoe is a half cylinder of length. Let's say that the length is 4 meters and radius 0.5 meters. Okay. So your canoe basically looks like this. So we're not worried about the hydrodynamic properties of the canoe. So there's the canoe, okay? And it's sitting in the ocean, all right? We'll say that it's sitting in fresh water. So what is the maximum mass that this canoe can hold? Okay. So basically, the idea here is that if the canoe is just about to go under, if it's just about to go under, then the volume displaced is going to be the entire volume of this half cylinder. Okay, so the volume displaced when about to sink is equal. So a full cylinder is pi r squared h, but because we have half of a cylinder, because it's only the top half of, the top half is cut off so you can sit in it. So the volume displaced is this, all right? And remember, the buoyant force is equal to the weight of the water displaced. So that means that the mass of fluid when it is about to sink is going to be the density of water times the volume, which is 1/2 pi r squared h, times gravity. So that's going to be, this is going to be the weight of all the fluid that is displaced, which is equal to the buoyant force. So basically, the maximum buoyant force is this. This is the maximum buoyant force when it's just about to sink. That's when the buoyant force is the biggest. If it goes any further than that, then all the water is going to rush into the sides of the canoe, and the buoyant force is going to then be reduced greatly. Okay? So the maximum buoyant force is this. Okay? So we have 1,000 times 0.5 times pi times r squared. It has a radius of 0.5 times h, which is 4, times gravity, which is 10. Okay. So that means that the maximum downward force before the boat will go under, before the canoe will go under, is about 16,000 newtons. Okay. And 16,000 newtons is roughly 1,600 kilograms. So that is the maximum weight that this canoe can hold before going under. All right, and that's including the weight of the canoe itself. So let's say that the canoe itself has a mass of 800 kilograms, then it could hold 800 kilograms in addition of passengers and other things, okay, and cargo. So let's review the idea behind that again. The maximum buoyant force is when the canoe is just about to be completely sunk. So what I did was I calculated that buoyant force, okay, and then if the mass of the canoe exceeds that maximum buoyant force, then it's going to go all the way under. It's going to go all the way to the bottom, okay. So that mass is 1,600 kilograms. There is one additional topic that I wanted to talk about, which is something called Pascal's principle. And Pascal's principle says that pressure due to an applied force is transmitted undiminished throughout the fluid. Okay? So pressure, if you push on one side of a container and you increase the pressure on one side of a container that's holding a fluid, then that pressure increase is going to show up on all the additional sides of the container. Okay? And so this is actually the idea behind hydraulics. This is the idea behind hydraulics, okay? So here is how hydraulics work, okay? You have and an important part is this Pascal's principle only applies to fluids in an enclosed space, okay? So if there is like a leak in your hydraulic system, then Pascal's principle is not going to apply. So if one of your hydraulic lines is cut, then your hydraulic system stops working, okay? But here's the idea, okay? Let's suppose you have a small cylinder, okay? And that small cylinder then connects to a bigger cylinder. Okay? And these two cylinders are completely filled with a fluid. Okay? So let's suppose that the area of the input is this, and the area of the output is this. All right? So, and then this is kind of like a piston. Okay, so this cylinder can slide back and forth. This cylinder can slide back and forth. Okay, so what if you apply a force F sub in at the input? Then the pressure at the input is going to be the force at the input divided by the area at the input. okay, that pressure is going to be transmitted to the output. So the fluid transmits that pressure all the way to the other side of the hydraulic system, undiminished. So that is also equal to the pressure at the output. So there's going to be a certain force on the output side of the hydraulic system. Okay? And so what that says is that the pressure at the output is going to be the force at the output divided by the area of the output. So the force at the input divided by the area of the input is equal to the force at the output divided by the area at the output. Okay, that is Pascal's principle. Okay, now notice how we have area at the output is bigger than area at the input. Okay, so if I rearrange this equation, and if I rearrange it, I get F sub in times A out over A in equals F out. So what I can see is that if the area of the output is bigger than the area of the input, like I have drawn here, then this ratio is greater than 1, and so the force at the output will be greater than the force at the input. So hydraulic systems, what they do is they change the radius of cylinders, basically, in order to affect multipliers on the force. So you can apply a small force at the input and get a really big force at the output. Okay? And so, and furthermore, it doesn't matter if your hydraulic system bends or does anything. So hydraulic systems are used all over the place. For example, in airplane wings, the flaps of the airplane are controlled by a hydraulic system, okay? And you can imagine that if an airplane is flying 500 miles per hour and you want to move the flaps, if you move a flap into the airstream, air traveling at 500 miles per hour hitting the flap creates a huge force. So you need to counter that force with the hydraulic system, okay? So that's what is done. You basically have the area at the output is connected to the flap. So you have a big force at the output, and you only need to apply a small force at the input, and the flap can hold at the position that it's supposed to be at. Okay? There have been situations where the hydraulic lines are cut, and so like if there's a break in the hydraulic system, like right here, for example, then the fluid is going to leak out and you don't have an enclosed space anymore, and then Pascal's principle no longer applies. And so then the force at the output becomes 0 and you can't control your flaps anymore. So that's really bad. If a hydraulic line is cut on an airplane, really, really bad, you will lose control of the flaps and you won't be able to steer the airplane anymore. So actually airplanes have redundant hydraulic systems. So they have multiple separate enclosed spaces so that if one gets a leak, then the other two can pick up the slack, essentially. So redundancy in engineering is important if lives are at stake or if a lot of money is at stake. All right, so I've kind of just gone over it. I think that you'll be able to figure out the problems in the homework. You're going to have to do. I haven't done every single type of problem that you're going to see in the quiz, but I think that you can figure it out. If you can't figure it out, please come see me during office hours, and I'll help you. Okay.